Hello everybody, my name is Alexander Knüppel from the Technical University of Braunschweig, Germany, and this is joint work with Thomas Thüm from the University of Ulm and my advisor Ina Schäfer, also from the Technical University of Braunschweig. So I want to talk about an idea which focuses on a particular challenge in the context of deductive program verifiers. Very briefly, it has a lot to do with the automatic proof search algorithm, which oftentimes depends on configuration options that have to be set manually. But let me first start with our context in general. So deductive verification is based on the idea of program verification with specified pre- and post-conditions. Typically, we have a set of statements which represent our program P. In this example here, we have a variable x, and if x is less than 0, x is negated. Then we may have a precondition, which in this case states that x equals a, and a postcondition, which states that x equals the absolute value of a. And the pair of pre- and postcondition is our formal specification of the program P. What we can do then is we can indeed define a proof obligation, which states whenever the precondition holds, so whenever x is a, and I run program P, my postcondition should also hold, which in this case is then the absolute value of a. And deductive program verifiers are based on some logical calculus to allow us to come to such a conclusion. We may then also say that program P is correct with respect to a specification. One such instance used for object-oriented code is design by contract, where we can annotate object or class methods with the already mentioned pre- and post-conditions directly in the source code. For example, for Java, we have JML, the Java modeling language. So imagine you're a software developer and you want to formally specify this Java method here. You could do that by using keywords such as requires and ensures, which correspond to the precondition and the postcondition. And we call this specification a contract, and hence the paradigm is called design by contract. One prominent deductive program verifier for Java JML code is key, although key can be regarded as an interactive verifier. I would say that most of the time the automatic proof search is the interesting part. So we as potential software developers would like to just write specified Java code and then run, for instance, key and hopefully get a correctness proof automatically. However, key also allows us to configure the automatic proof search. So to enable specific proof theoretical configuration options to kind of push the proof search in the right direction. And this is also pretty common in other domains, for instance, in model checking, where a lot of the internal algorithms are controlled by some parameters that we as developers or users, practitioners have to set. So what that means is we as developers face the problem of suboptimal configurations. And in fact, key in its current version comprises roughly, so the current version is 2.7, comprises roughly 500 million different combinations of configuration options, if we count all the configurations that could possibly be altered. Obviously, not every change makes sense, but it is also not easy for people to always get a feeling for when an option must be changed, because it may require deep knowledge about some internal behavior. Finally, now comes the interesting part. Choosing the right configuration influences two dimensions. One is provability or verifiability. So sometimes a contract is not automatically provable with key, for instance, because of the applied configuration. But it also influences the effort, either time or proof size, for instance, that our prover, for instance, again, key, needs to find a proof automatically. And in a software engineering context, we would like to choose a configuration that leads to faster verifications, but also allows us to prove a verification task automatically. Very quickly, here's the options pane of key, which only covers some of the parameters for keys proof search strategy algorithm which tries to automatically find a solution. There are some more parameters where we can also decide to some degree what we want to prove, for instance, if we care about integer overflows. But only for the proof search strategy here, or for these option panes, we can already decide between 140,000 different configurations, which makes it, as mentioned, very difficult to find the right configuration if you are not an expert. And these tools also evolve over time, so it's likely that more options will be introduced, and this can lead to slight confusion for practitioners, developers, who not always get the idea of certain parameters and when they are needed. And in this case, also tooltips in the documentation often also require some expertise in proof theory. So back to this example that we had before, we may hit the verify button in key, and Key's automatic algorithm tries to solve this problem here, and we might actually get a negative result. We might be a little bit puzzled here because the specification looks actually pretty good, and after some time we might identify the problem. There is actually a parameter which is called proof splitting, which we seemingly set to the wrong option. In this case, off. When we change its value, Key can indeed automatically prove the method. So the problem here is, as a software developer, we might not really know what the parameter does and what it is used for, but it is indeed very important for automation. So coming back to the big picture, I think everybody can relate to this, that human-machine collaboration is many times required for the tasks and problems you face, so to speak, for interactive theorem proving. But it is also necessary to lower the hurdles for beginners in a way that we can decrease interaction in program verification and increase automation. And improving this configuration part seemed to be a good opportunity. And there are also more configurable program verifiers, not only Key. So the question for us was basically, how can we find a good configuration, so a configuration that increases automation without being an expert in proof theory? And how can we generalize this idea approach so that it is not only applicable to Key, but maybe also to other program verifiers? And how can we build some tooling around it? So we thought about how we may get a better understanding of the influence of the parameters. And we thought maybe it is a good idea to incorporate actual domain knowledge of experts. So instead of calling an expert to get help, how about channeling the expert knowledge in some form to make it accessible for everybody at any time? So what we propose here is to formulate hypotheses about how certain parameters that we can choose may influence the automatic proof search in the 2 dimensions I mentioned before, which is verifiability and verification effort. And the nice part about hypotheses is that they can also be tested with statistical tests to see whether the respective hypothesis holds. So not only are we channeling domain knowledge, but we are also able to sort out false assumptions. But to do so, we also need to collect a certain amount of data though. Okay, what do we mean by hypotheses? Well, as mentioned earlier, we consider 2 dimensions here, verifiability or provability and verification effort. Examples of hypotheses may then look like these 2 examples here. For instance, for verifiability, we might define a hypothesis that says whenever a specification case or verification task is provable with some option OA, it is also provable with an option OB. With other words, OB is at least as effective than OA. A different example focusing on the verification effort may state only in the presence of loops, choosing a specific option compared to another one might lead to an improvement in the verification effort. In fact, we have a couple of language and specification constructs that allow us to make certain hypotheses more precise. Okay, so to automate most of that, we came up with a framework that we coined Guido, based on the word guidance, but which is also a German name. Guido is also implemented and enables us to dive a little bit deeper into this configuration issue by allowing us to test different models and metrics. But let me quickly go over the workflow, so all the parts that Guido combines, and afterwards I go a little bit more into detail. So Guido is divided into two phases. First, an offline training phase, as also used in machine learning, where we create a cost model for particular configurations. And second, an online configuration search, which uses the model and an input verification task and then predicts an adequate configuration. In the offline phase, a user, typically an expert, starts by defining a set of hypotheses, which is essentially a big chunk of domain knowledge. And second, we establish a data set of verification tasks for which we use a program verifier. And finally, as experts may have certain assumptions about how specific parameters may influence the verification result, which can also turn out to not be true, we apply statistical hypothesis testing to find out which of these hypotheses we can actually accept and which we should ignore. The result is then a cost graph for each parameter, where some values obtained in the statistical tests flow into it as well. In the online configuration search, we then construct a linear optimization problem, which also depends on the structure of the input program, and then try to find optimal configurations, or the optimal configuration, and apply it to the input verification task. So all in all, it is not so much different from some kind of machine learning, but we use actual domain knowledge to hopefully improve our models while also needing not as much data, which is honestly not easy to get, and it may also take a lot of time in this formal verification context to actually verify tasks in the first place. To be a little bit more precise or specific, we created a domain-specific language that allows us, for a given verification system, to define hypotheses in a convenient way. So in this example, we use Key in version 2.7 and define a hypothesis on the parameter of proof splitting, where we assume that the option delayed outperforms the option off whenever we have if constructs in our verification subject. Next, we want to establish the dataset to prove our hypotheses. We have our big configuration space, as mentioned before, the 140,000 configurations, for instance, and we perform some sampling to significantly reduce the number of configurations. In this case, we use pairwise sampling, which means that between two options of different parameters, there exists at least one configuration that has both in it, none of them in it, and exactly one of them in it. And for Key, roughly 2,000 different configurations are enough and remain. And then we apply each remaining configuration to each training verification task that we have, and store all parameters and values for later usage. And finally use that data set to test our hypotheses. For each parameter, we then construct a cost graph where nodes correspond to the possible values of that parameter. So here we have a parameter P, which can be set to either O1, O2, or O3, and directed edges are added whenever we have a hypothesis between two options. And the direction reveals which option is essentially the one that improves the verification. Additionally, we have individual edges for hypotheses regarding verifiability and regarding the effort. And the weight itself of an edge is a metric that represents how strong we believe the hypothesis holds and is computed from the tests themselves. Afterwards, we construct a linear program which we try to optimize. I won't go into too much detail, but we have essentially two distinct values, which are these thetas here, and they combine the value for how likely it is that a specific configuration option O improves either verifiability or the verification effort. And with this gamma, which is a user-defined parameter between 0 and 1, we can control if we are more interested in finding configurations that will probably decrease the verification effort or that increase the potential of verifying a task automatically. For example, if we set gamma to 0, we are only interested in the performance or verification effort. Okay, I will now present our initial results. Not all made it into the short paper, but it's also ongoing work, so I think it's adequate to share the direction we are going right now. In particular, we collected 94 verification tasks, differing in size and complexity. So for a better evaluation, obviously we would like to use more data, but nonetheless, I will now discuss 3 research questions we answered using these 94 tasks. First, we wanted to investigate whether increasing the likelihood for more performance-oriented configurations also decreases the likelihood for automatic verifications. Essentially, what can we say about this parameter gamma, and is there a trade-off between performance and verifiability? Second, we surely wanted to know whether Guido can outperform a usual strategy, which starts with a default configuration and then randomly flips configuration options. And third, are we actually able to reduce the proof size of our verification tasks, which can also be an important performance metric if we think about proof replay or proof carrying code. Very briefly, here are some of the statistics from the offline phase. We divided the 94 verification tasks into 90% training data and 10% test data. And we run the experiments a couple of times on different training data and test data. And that is also why we could accept between 30 and 34 hypotheses, depending on the current data set. So the following results are therefore also average values. So to answer question 1, we have a figure here. We essentially set our gamma between 0 and 1 on the x-axis and illustrate with the red line the percentage of successful verification attempts. So gamma set to 1 means also that we only concentrate on verifiability because we do not focus anymore on hypotheses that are concerned with the effort. And we can see that the red line rises quite significantly. The blue line is a little bit more complex. With the blue line, we illustrate how much of all tasks were performed the fastest using a specific value of gamma. So when we look at gamma set to 0, we see that the majority of tasks we could solve, which are only 25% of all tasks revealed by the red line, were solved the fastest with the computer configuration by Guido. So there seems to be really a linear trade-off. So it is unlikely to improve both dimensions with a specific option, or at least very few options seem to be capable of doing that. So to conclude, it is a good idea to balance the 2 dimensions and then maybe to adapt gamma if needed. For question 2, we measure the performance. Here we use the trial and error strategy, which starts with the default configuration of key and in case of failure, flips the parameter randomly and does so until a specific timeout is reached. We also use the time spent during the verification as a measurement for the verification effort. We can see that Guido, here illustrated with the blue line, spends less time, so on average roughly 25 minutes for all the tasks it could solve, compared to almost 42 minutes, which was needed for the trial and error strategy. Additionally, Guido also closed 2 more tasks during this evaluation. Finally, for the last question, we wanted to see whether we can find smaller proofs, and again compared Guido with the trial and error strategy. And what we identified was that not a single proof that we found using Guido was larger. But in fact, we could easily reduce the proof size of 14 verification tasks. And we did that by only setting gamma to 0.5. So all in all, with Guido, we combine quite a number of complex topics. Most importantly, there's not really much research going on in this area. There's some research going on in the model checking domain, and there are a lot of heuristics there, but not so much in the area of theory improving. So we are also kind of curious in which direction this field will develop and whether we can generalize our ideas to more tools. And we strongly believe that integrating domain knowledge can be a very important factor, and we think a framework like Guido also helps to test out new ideas, new metrics, new models, and new computations, and can also be employed by tool builders as benchmarking tool to see whether the assumptions about certain configurations are actually correct. Okay. So this concludes my talk, and thank you very much for listening.
Okay, so we are live. So thank you, the authors. And now it's time for questions, and I see there are already 3 on the deck. So let me start reading the first questions. Oh, we have both authors. Okay, so the first question from Simon says, do you have any way to guarantee that the initial set of programs is representative of those to be verified in real life? That is, that you do not introduce bias in the expert knowledge.
Yeah. So first of all, thank you for that question. I think that it's always a problem with data, that it's most probably biased in some way. So I can only speak for our study, which obviously was a little bit smaller, that we tried to use as much language constructs in our examples, like loops, if constructs, and so on, to kind of reduce the bias a little bit. We use large and small programs, but then again, we only used toy examples here. So I would expect if someone wants to use that in a more professional setting, that they would already come with some benchmarks that they're very familiar with, and they know for which programs they want to apply verification, and they would use would use that data for that. So actually, no, we have no. Obviously, we have no way to guarantee that it is not biased for our expert knowledge. So
thank answer to Simon's question, but in case I think he can follow up in the chat. Then there is a question from Marie-Christine, and the question is, how difficult is it to transfer your approach to another verification tool?
Yeah, that's also a very good question, and I think that's one of the selling points of Guido, because it doesn't look at the algorithm itself, but it's an external approach that one can just apply to different verification tools. And we have an implementation for that that comes with an API, and there are a couple of steps to do. Like one has to model the configuration space of that verification tool. For instance, key differs from other tools like pharmacy in terms of the configuration options we have. But if we have that and we have the benchmarks that we can use, the rest is almost can be done automatically. What is needed is some sort of API bridge, or to call it verifier. That has to be developed. But then we try to minimize actions needed to transfer our approach to other tools. But I have to say, the tool is not open source quite yet. I will polish it a little bit and will then publish it, because we only did a small study right now. And but in the near future, we will probably publish that tool. Thank you.
Thank you. So follow up, just feel free to type it in the chat. And then we have another question from Robert. And the question is, you mentioned that your verification task came from 4 different projects. Are your results consistent over all 4 projects, or are your results consistent over all 4 projects, or do some perform significantly better than others with your hypothesis?
Yeah, so again, all projects have in common that they consist mostly of small quote-unquote toy examples, so smaller examples, and these were very much consistent. I think I mentioned that we could accept between 30 and 34 hypotheses, depending on the tasks we used. But the projects in general, they were very much consistent. But then again, we did not. So we have our assumption that we at least can verify all the subjects we have automatically with 1 configuration. So this was assumption that we have automatic verification. And most of the time for larger programs, interaction is still needed because the specification is not good enough. So yeah.
So thank you. I see there is a comment from Simone that is a follow-up takeaway about your answer to the first question. So if you want to read or comment on this, and if anybody has any other questions, just feel free to type them in the chat. In the meantime, I actually have a question. So to answer to research question, you build your research question in a way that you basically compare your performance with the performance of like picking the configuration randomly. So I actually have a couple of questions about this. How it is really this is realistic, and like how is actually done in practice from novice? So do you have any insight of this, like, you know, which are the strategy that novice usually use? And then how you can find this in general out if you don't know? And then, and this is a full question, this is the same one. And then whatever is the other strategy, how do you think that comparing with another kind of like maybe a little more realistic strategy, the result that you obtained?
Yeah, thank you for the question. How realistic is that? So what is integrated in this other strategy is also the default strategy. So the default setting, key comes with default settings that work quite well for a lot of programs. So in this regard, we could already see that we can outperform the default strategy. And then we try to randomly pick 1 configuration option. It's very hard to come up with a comparison of how a human being would try to solve this by trying out different configurations. So this was the simplest comparison strategy that we could think of, and we tried that. So, but because we have this comparison with the default strategy, we think it's quite valuable to go in this direction further. A more realistic algorithm, yeah, what would that look like? Kind of like a greedy strategy or something like that, but it's very hard to design because there's always bias involved from our side to design a different approach. So what we would need to do, basically, I think, is conduct a user study, which is also very difficult to do in this case. So if someone has an idea, I'm open to that.
Yeah, when you were saying, like, I was thinking a way would be like a very long data collection of people, you know, novice doing it, and then like try to figure out, like, learn from that to have this as a comparison. But yes, it's a gigantic work. So I understand your resistance to going, of going in that direction.
There's always complaints and arguments against other strategies. So this is always not that easy. So we try to stick it easy for this time, and but we will try to improve on that and try other strategies. Also evaluate how much hypotheses we actually need, or how less hypotheses in this regard. And yeah, but there's a lot to do.
Thank you, Alexander. Before we just move into the other room. So Alexander will be available for discussion in the discussion room. I want to thank you, everybody, for being in this session, for this tree talk. And if you're interested,